Okay, so number 20 is one of these fun problems where they give us the table of data where we watch concentrations of different things change over time, measure the rate, and figure out what the rate law is based on those data. So, we need to figure out what the order is for each of these three reactants by picking two experiments where that reactant has changed its concentration, but the other two stayed the same. So if we look at A and compare experiments 1 and 2, we can see that we quadrupled the concentration. And when we quadruple that concentration, the rate also quadruples. So A is going to be first order. So when we quadruple the concentration, we quadruple the rate. For B, then, we can compare experiment 1 and experiment 3, because it changes concentrations, but the other things stay the same. And we triple it. And when we do that, the rate stays the same. So we triple B, and the rate stays the same. So B is having zero impact on the rate. So it's zero order. And then for C, we can compare experiments 3 and 4. And we can see there that the A stays the same between those two experiments, B stays the same between those two experiments. But here we've tripled our concentration of C. And when we do that, we increase the rate by a factor of 9. So this is going to be a second order because it changed by the square of what we changed the concentration by. And so we can simplify this rate law down to just K times A times C squared, which is answer choice A. And if they asked us to solve for the K value, we would pick one of those 4 experiments, whichever one's your favorite, plug in those concentrations, set it equal to the rate, and then solve for the K value. Number 21, they want us to figure out which reaction has an increase in entropy, so a positive delta S. And so we're going to look primarily at the phases of the reactants and compare it to the phases in the products and see which one becomes more entropic. And so we know gas phase has the highest entropy by a long shot, and solid is the least entropic phase. And so in A, we go from 3 moles of gas down to 2, so that would be a decrease in entropy, so it's not A. B, we go from aqueous to solid. Solid is low entropy, that's not going to be the answer choice. For C, we go from 2 moles of gas to 1 mole of gas, so that's a decrease. In D, we go from aqueous and we make some gas and liquid. And though making that water is technically a slight decrease in entropy, making the CO2 gas is such an increase in entropy that this would really be the driving factor. And this would be an increase. And then if we look at E, we can see we trap some gas in a solid and just make more solid. And so that's going to be a decrease in entropy also. So D is the correct answer. Okay. So here in number 22, we're calculating the pH of an ammonia solution. And they give us the Kb. So we have to write the reaction for what happens when we put ammonia in water. So ammonia is a weak base. So we'll take a proton from the water to make NH4+, which will be aqueous. And it leaves behind aqueous hydroxide. Okay, and so water is a liquid, so we're not going to include it in our equilibrium expression or our ice table. we can go ahead and say we have 0.5 molar of the ammonia initially, 0 of our products. So we're going to add X to both of our products, and we'll use up X from the reactants. So 0.5 minus X. So we can set up our Kb expression, which is going to be products over reactants. So we'll have our NH4 plus times the hydroxide divided by our NH3, which is going to be X squared divided by 0.5 minus X, which is equal to our Kb, which is 1.8 times 10 to the minus 5. And we say that Kb would be small enough to ignore any added or subtracted X's. And then we can multiply over and take the square root to solve for X. And so when we solve for X, we get that it is 3 times 10 to the minus 3 molar. And if we look up at our ice table, the X is corresponding to hydroxide concentration. So when we take the negative log of that value, what we're going to calculate is pOH. And here we can see that the pOH is equal to 2.52. And so to get pH, we'll have to do 14 minus 2.52, which is equal to 11.48. And we started with a weak base, so it makes sense that this pH is greater than 7. And so we can go ahead and choose that answer choice, B. Okay, so for number 23, we have a reaction coordinate diagram. And they want us to figure out how many transition states, intermediates, and whether this is really endergonic or exergonic. And so here we can see our delta G is denoted by products minus the reactants. And so we have a decrease in energy. So we would say that this is exergonic. Okay, and the number of transition states. The transition states are going to be at points B and D here, when the molecules are at their highest energy states as they're twisting and really uncomfortable twisting into the products. And then the intermediate is going to be represented at point C, and that's just what we are left with between, or at when step 1 is done and step 2 is beginning. Okay, so the answer choice here will be C. Or I'm sorry, D. And so here we're using that same reaction coordinate diagram, and I want us to figure out which of these mechanisms could possibly correspond to this diagram. And so we know from looking at this diagram that the first step has a huge activation energy compared to the second step. So we would say the first step is going to be the slow step, and the second step is going to be fast. And so because of that, only mechanism 1 would apply, because we know we have 2 steps, so 3 is definitely out. We know, not mechanism 1. We know that our first step is slow, so we want to pick the mechanism that has the slow first step and the fast second step. So mechanism 2 is the winner. For number 25, we're going to pick which of the following salts would have a basic pH. So we're going to pick the basic compounds. And so we can think that calcium carbonate would dissociate into calcium ions and carbonate ions. We know calcium is a spectator, but carbonate ions are conjugates of carbonic acid, which is a weak acid. So carbonate would be a weak base. So dissolving calcium carbonate would raise the pH of the solution. For this iron nitrate, we'd get iron 2 plus and some nitrate ions. We know the nitrate is a spectator. And if anything, this iron is a Lewis acid, a pretty good Lewis acid, and so that would decrease the pH of solution. So it's not 2. For barium chloride, you would get barium ions and chloride ions. And these are both spectators, so dissolving this wouldn't change the pH at all. For option choice 4, we would dissociate into sodium ions and acetate ions. We know sodium's a spectator, but acetate is the conjugate of acetic acid, which is one of our weak acids. So acetate would be a weak base. And this would raise the pH. For the 5th choice, we dissociate into K plus and Cn minus. We know potassium is a spectator. Cn minus is the conjugate of HCN, which is a weak acid, so cyanide would be a weak base and would increase the pH of solution. So the answer choice here is 1, 4, and 5, answer choice E. For number 26, we have the Haber process again, and they give us delta H and delta S for the reaction, and they want us to figure out at what temperature the reaction switches from being spontaneous to non-spontaneous. So we know that a negative delta G is spontaneous, and a positive delta G is non-spontaneous. And so where they're going to flip between those two is at point when delta G is equal to 0. So we can use 0 for delta G and then solve for temperature. And so if we say 0 is equal to delta H minus T delta S, we can rearrange to say that T delta S is equal to delta H. We can divide and say temperature is going to be equal to delta H divided by delta S. So we're just going to plug in delta H and delta S, but we need to make sure the units match, because enthalpy is given in kilojoules per mole and delta S is given in joules per mole Kelvin. So I'm going to leave enthalpy in kilojoules at negative 92.4 kilojoules per mole divided by, now I'm going to change my entropy to kilojoules. So this will be negative 0.1983 kilojoules per mole Kelvin. And now when I compute that, I'll get the temperature and it will pop out in Kelvin. And it is 466 Kelvin. So below that it will be spontaneous, and above that it will be non-spontaneous. So number 27, someone shows up at the hospital not feeling well, and they do blood work and measure the concentrations of carbonic acid and bicarbonate, and they want us to figure out the pH of that patient's blood. They give us 2 Kas, and so here I've expanded those Kas to show what they really represent, which is the sequential loss of protons. And so hopefully you can see that the equilibrium that has both of the molecules of interest here, that we're given information about is the first equilibrium. And so we're going to use Ka1 to think about how those two are related to each other. And so what they've given us is this weak acid, carbonic acid, and some amount of its conjugate. So we have weak acid, conjugate base. So we have a...
Buffer alert! Buffer alert!
Buffer! And we can use Henderson-Hasselbalch equation, which is pH equals pKa plus the log of our amount of base divided by our amount of acid. And we're just going to use pKa1 to solve this. And that pKa1 is 6.36. So we can go ahead and set this up. 6.36 plus the log of our base, which is going to be the HCO3 minus. So we can just use 19 millimoles per liter, divided by the amount of acid, which is 2.7 millimoles per liter. You can see we have more of the base around, so our pH is going to be a bit higher than what the pKa is. And that pH ends up being about 7.2, which is a little lower than physiological conditions, so it makes sense that maybe they're not feeling so well.